Hello, my name is Henry Elijah Craig, and this is my Physics 2212 Lab 4 on circuits. The purpose of this lab was to use the principles of energy conservation, also known as the loop rule, and the current conservation to predict behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. The first part of this lab dealt with a circuit that looks somewhat like this, where we had a current 1 and a current 2, and we predicted that current 1 and current 2 would both be 0.02 amperes, just using the resistance, well, the net resistance shown by the two resistors and the voltage of the batteries. And we also discovered that if you flip an ammeter, it causes the current to change signs. So 1.99 amperes becomes negative 1.99. And the recorded values from the ammeters were the same as what we had predicted. We also experimented with this and replaced one of the ammeters with a voltmeter. And the voltage from the voltmeter read as 3 volts. And that was because the voltage from the two batteries added up to 3 volts. And the remaining ammeter would read a current of 0 because the circuit would be incomplete and the current would not be allowed to flow through. And that is because an ideal voltmeter, which is what we were using here, has an infinite resistance, so current is not allowed to flow through it. Each voltage reading is shown here throughout the different sections of our circuit. And the current is constant at 0.02 amperes, and the sum of all the voltages is 0 volts since this is a round-trip circuit. So you can see at the batteries we have a voltage or potential difference of 3 volts, and then when you get to the first resistor, it drops a little bit, and then the second resistor drops the rest of the way down to 0. And so the net difference is 0 because this is a round-trip circuit. Here's that graphically, and you can see as you go through the batteries, the total voltage goes up to 3 volts. Well, first it goes up to 1.5 volts, and then 3 as you pass through the second battery. And then it drops at the first resistor, and then drops the rest of the way down at the second resistor and stays constant at 0. The current reading does not change when the voltmeter is attached in series because an ideal voltmeter does have infinite resistance, so no current can pass through. But if we put the voltmeter in parallel with the 100 ohm resistor, the ammeter reads 0.06 amperes because you are taking current away from the resistor, and it allows it to pass around. So here are the calculated values for the resistance of both resistors, the wire and the ammeter. We know that the wire and the ammeter both have no voltage going through them or no potential difference. And so their resistance is going to be 0. And the other two, we just took the voltages and the potential difference across the two resistors and divided that by 0.02 amperes to get the final resistance. The second part of this experiment, we used and experimented with an RC circuit or resistor capacitor circuit. So at first we used a 10 ohm and a 20 ohm bulb, a 9 volt battery, and a 20 millifarad capacitor. And with the 10 ohm bulb, the charge time was around 22 seconds, and the discharge time was just under 15 seconds, and both of those increased with the 20 ohm bulb. And when charging and discharging the capacitor, the bulb's light shined really bright at first and then slowly died out, and that's just because the capacitor is either the charge that is being applied to the bulb or the capacitor is being charged as the bulb is shining. And the rate of change of the voltage going to the bulb is time dependent. And so we have a differential equation of Q over RC plus dQ over dt is equal to 0. That is representative of the the time dependence of the voltage. And that can be simplified down into this top equation here, which gives us a way to find this value of RC, or the time constant, where the voltage difference has dropped to 1 over E of its original value. And that becomes a plot of the natural log of delta V over V naught against time, which gives us a straight line with a slope of -1 over RC. And here we did that. We took that slope using a 30 ohm bulb and 20 seconds worth of discharge data. And with a slope of negative 0.166, our RC value equates to about 6 seconds, or about 6. And this makes sense with the data we collected. Now, the real world applications of this, if this experiment were done in real life, the values calculated would be slightly different, but not necessarily enough to dispute any claims we've made. And that's because real ammeters and voltmeters have variables to account for. And we were using ideal tools in this experiment. And if we used a real battery, our model would have the same predicted time to charge a capacitor, but it may not be as close to said predictions to discharge the battery, or due to the discharge of the battery.